Hey guys, it's Mr. Krieger. Today I'm going to do some review of the calculator functions. Now, it's not essential that you know how to use the calculator on this version of the AP statistics test, but it's still probably advantageous for you to know it because whatever calculations you do have to do without the calculator, you can check with your calculator. So it'd probably be wise to know the basic functions. Okay. So let's say you want to find basic statistics, mean, median. The quartiles. That's the 5-number summary. You could put your. I'm not going to do this right now, but I'll just show you where you would go. If you go to stat and enter, which is edit here. You can type your data into L1, especially if you're doing one variable statistics like finding the average or the median for a specific group of grades. You put these numbers in a list. Then once you have the numbers in the list, to get the one variable statistics, you go to stat, calc, one of our stats, and L1 would be, getting you all your one variable statistics. In fact, I have a data set in here. I'll just run it. It's not the same data set you see here, but I'll just show you like X bar is the mean and sigma sub X is your standard deviation. Here's your 5-number summary. The minimum value, the maximum value, Q1, the median, the Q3. So there you have the values that you would use for your box plot. We'll all take a look at how the calculator compute the box plot for you too right here. Again, if you're going to do a box plot and you want to actually see what it looks like, it's again one variable stats. So you could go to, you obviously put your data in. Then you're going to go to second y equals, which is the stat plot. And you can put on, so you have two types of box and whisker plots here. This one will show you the outliers and this one won't. You got to put your plot on. Oops, let me go back to that. So, I'm going to go scroll over to the one with the outliers. L1 is where our data is. And then we could do zoom 9. And that will show you a box plot. And if you do second trace, actually not even that, if you just go to trace and you just keep moving over, it will show you the values, like Q1 is 498, median is 542, etc. This was that data that I have in the calculator already. It's not this set of data. Okay, that's how you get to the box plot. Histograms, again, it's one variable stats. Same thing, go to stat plot. Histogram is that, in the type, it's that third choice. And again, if you go to zoom 9, which is your stat plot, show you a box plot. And if you want to change like the minimum or maximum that you can see, or change the width of the bars, if you go to window, let's say I want to go from minimum to be, let's say, 400 to 800. And let's say I want my scale to be 50s. I can now go, don't hit zoom 9 now, just go to graph. It will change the view, will change your lowest and highest values, and also the intervals, the size of the width of these boxes. Okay, so it's easy enough to do that. Move ahead to the normal distribution. This is how to use the normal CDF and also the inverse normal stuff. I'm actually going to go through a few problems with you so you can appreciate it better. So let's take a look at this. Suppose we want to calculate now. Just before we go ahead, you could use z-scores, or you could actually use the raw data they give you, as you'll see what I mean. So let's say you wanted to compute the area to the right of a z-score of 1.11. So what that means is if you have a normal distribution, your mean, in the standard normal distribution, your mean is 0. So z of 1.11 is here, and we're really looking for the area in that tail. You know how to do this already. You go to, it's in the distribution, so second vars, normal CDF, we're going from 1.11 to infinity, which is E99. You get to the E by doing the second comma. And again, we're using a z-score, so we're doing the standard normal with a mean of 0 and a standard deviation of 1, and that's going to give us 0.13, about 13% area in there. Okay, and let's say we want to do the area to the left of a z-score of negative 1.93. So that's going to be like over here. and we're talking about the area on this tail. So it's going to basically be the same thing. I don't know if you need me to go through this, but I'll do it quickly. So again, normal CDF. This time we're going from negative E99, which is like negative infinity, to negative 1.93. Again, we're using a z-score, so 0 and 1 will be your mean and standard deviation, and here you get 0.027. 0.027, so it's about 2.7% of the area in that tail. And then we can do the area between two z-scores, and it's obvious, you know, you would just go to normal CDF, and you'd put in the low value, which in this case is 2, to the high value, 2.47, and you could paste that, and it's about 1.6% or 0.016, okay? So it's pretty easy. Now, the opposite case is not to find the area in a tail or in between values, like this last one we found the area between two values, for example. Suppose we want the z-score associated with an area. Now we're going to use this inverse normal calculator function. Just be aware that what's going to be is to the left of 0.7123. That means 71% about of the area is in here. This is the 0.7123, and we want to find this z value right here. So if we go to second distributions, this time we'll go to inverse norm. The area is 0.7123, and bear in mind that it's always going from the left to the right. So it's always going from negative infinity to whatever that area is. And again, 0, 1, because we're using the standard normal. And it's going to tell us that the z-score is 0.56. So z is 0.56, which, just so you can keep in mind, 0 is here, so 0.56 is actually to the right of the mean. All right, so now let's actually try a couple of real problems out so you can understand what we're doing here. Is cholesterol a problem? The level of cholesterol in the blood is important because high cholesterol levels may increase to a heart attack, heart disease. So the distribution of blood cholesterol levels in a large population of people of the same age is roughly normal. For 14-year-old boys, the mean is 170 milligrams per deciliter of blood, and the standard deviation is 30. Levels above 240 may require medical attention. What percentage of 14-year-old boys have more than 240 milligrams per deciliter of cholesterol? So the diagram is going to look like this. We don't need to do a z-score. We could if we want, but we're having a mean of 170 here. And what we want to see is we want to see the percentage that's above 240. So I'll show you how to do it both ways. Let's say I wanted to do it straight from here. All we need to do when we go to our normal CDF, we're going to go from 240 to infinity, E99. And we're going to put in the mean that we have, which is 170, and the standard deviation they said was 30. And let's see what that gives us. That gives us less than a percent. It's just about 1%, 0.0098. So it's just about less than 1% of the population of 14-year-old boys is at risk of having high cholesterol here. Okay. What if we wanted to do it the z-score way? Simple. We'd make our z-score by doing x bar minus mu over sigma, which in this particular case, x bar was 170. Let's see, x bar. Oh no, I'm sorry, my mistake. The x bar was 240. The mu, the mean is 170 over a 30 standard deviation of 30. That's giving us 70 over 30, and 70 over 30 is 2.33. So z equals 2.33 repeating. So now if I wanted to find out the area, it's obviously going to be the same area, but just to show you what it's going to look like, when we go to the normal CDF, instead of doing from 240 to infinity, we're going to go from a z-score of 2.3 repeating to infinity. But now we're not going to use the real mean and standard deviation. We're going to use the standardized 0 and 1. And you'll see it's the same exact value, 0.0098. All right, and this says to use the table. Never use a table. You have technology, and obviously, you know, you always have to write down a conclusion in the context of your problem. So we could literally say that in this case, like less than 1% of all 14-year-old boys would have a high cholesterol level of 240 milligrams per deciliter or more. Okay. Okay. Another problem involving the normal distribution. Okay, to qualify for the police academy, candidates must score in the top 10% on the general abilities test. The test has a mean of 200 and a standard deviation of 20. Find the lowest possible score to qualify. So you want to see what you need to get into the police academy. Now, let's just stick with, instead of changing to z-scores, we can use the actual values. We know the mean is 200, right? What we need to find the z-score that puts us in the 90th percentile, the top 10% get in. So this area in here has to be 0.90. So if I'm looking for a z-score and I have the area I need, then what I'm going to do is I'm going to go to the inverse normal. I'm going to put in the area, which in this case is 0.9, 90th percentile. Mean is 200, and standard deviation is 20. And that's going to give me an actual value of 225.63. So essentially you need like a 226 or better on this test in order to qualify for the police academy. Okay? All right, this is also one more example of the normal distribution. We'll move on to something else. A tire manufacturer believes that the tread life of its snow tires can be described by a normal model with a mean of 32,000 miles and a standard deviation of 2,500 miles. Okay, so answer these questions. If you buy a set of these tires, would it be reasonable for you to hope that they last 40,000 miles? So again, the mean amount of time they last is 32,000. So 32,000 here, right? We want to see if we can get our tires to last 40,000 miles. Let's see what percent of the tires would last 40,000 miles or more. So well, all we need to do is go back into normal CDF. We want to go from 40,000 miles to infinity. We want to see what percentage of the tires last that long. But we're going to put in, we're not going to use a z-score, we're actually going to use the 32,000 and the 2,500 standard deviation. And we're getting a really, really small score. I have a scientific notation here. It's like 0.00068. It's far less than 1%. It's less than like 0.1%. So what we're talking about here is it's not really likely to happen. It would be a rare occasion, especially 4 tires to last that long. It's not likely, so that shouldn't happen. Okay, what proportion of the tires can be expected to last less than 30,000 miles? You know how to do this already. Again, you have this. You're talking about your mean is 32,000, so you're talking about 30,000 or less here. Approximately what proportion of tires can be expected to last between 30 and 35,000 miles? So again, here's your mean, and 32 is the middle, and you want to go from 30 to 35, and you'd be finding that area in there, no problem. I think you got no problem with that. All right, now the D and E are good questions. Estimate the IQR, the interquartile range of the tire's tread life. All right, so we need the values at the quartiles. So basically, 25% of the data should be here. So we want to find the tread life with 25% of the data here. And this upper value is 25%, but we want a value here that will have an area of 75%. That will mean the equivalent of having a upper quartile, including 25% of the data. So what we're going to do is we're going to go to second vars. We're going to go to inverse norm. We want first area of 0.25, but we're going to put in the actual values here, 32,000 and 2,500, and the lower value is going to be 30,313.77. So this lower value here is 30,313.77, and this upper value, I'm going to go and I'm going to put in from, negative infinity, no, wrong place. I want to go to inverse norm. So this time I want to go from negative infinity to 0.75, and I want to put in, no, I keep picking the wrong thing. Inverse norm. All right, area is 0.75, mean is 32,000, and standard deviation is 2,500, and that's 33,686.22. And you should know that anytime you're talking about a range, we're not talking about literally low to high. You're talking about the difference of these two numbers. So you're going to have to do 33,686 minus 30,313, which I can, since they're already here, I can do this minus this. And we get the interquartile range, the IQR, is 3,372.45. Okay? Finally, in planning a marketing strategy, a local tire dealer wants to offer to any customer whose tires fail up to a certain number of miles. However, if the dealer is willing to give refunds to no more than 1 in 25 customers, for what mileage can he guarantee these tires to last? So he only wants, obviously, the tires that are lasting the least, those tires he's willing to give people their money back. But we only want to give back money to the only 4% of the customers. 1 out of 25 is 4%, right? Or 0.04 proportion, right? So we're talking about an area here of 0.04. These are the tires that were the worst of the batch. They didn't last as long as they should have. What mileage should he tell his customers if they get this mileage or less, and then their tire fails or wears out and they have to replace them? What mileage should he tell his customers that they could bring it back and he would give them a refund? So again, we're going to go to the inverse normal, and we're going to put in 0.04. Keep the mean and standard deviation, and we're getting 27,623. So I'd probably round it down to I'd say if you get less than, let's just say this. If you get less than 27,000 miles, 623, then I'll refund your money. All right? So this is going to be an inverse norm question. All right. By the way, what I did here for the normal distribution, you can do the same thing for the t distribution. Notice that there's a inverse t and a t-CDF. Inverse t is like inverse normal, and t-CDF is the same as normal CDF. The difference is you need to know the degrees of freedom. That's the main difference. Degrees of freedom is always the sample size minus 1. Okay, so other than that, it works the same way. All right, now in terms of scatter plots and linear regression, this is the data that I actually have in the calculator. What we have going on here, because I'll show you how to make a scatter plot and also how to run the linear regression. Whenever you're doing linear regression stuff, you should really turn your diagnostics on. Your diagnostics you can find in the catalog, which is second 0, and then scroll to diagnostics on. Or if you go to mode and scroll down to the bottom thing, it says stat diagnostics, make sure they're on. Okay? That way you get your R value, correlation coefficient, or R squared coefficient of determination. So that will be available to you that way. Let's say we wanted to see a scatter plot of this data. Again, I typed this data into L1 and then the corresponding data into L2. So you know what's going on here. What they noticed is that the more powerboats there are, the more manatees were killed, because obviously the more boats in the water, the more likely the manatees are likely to get caught in the motor or something, in the propeller, and get hurt or killed. So we want to see if there's a correlation. Well, we want to see what the correlation is. We're going to run the scatter plot. We're going to look at the scatter plot. So that's going to be in stat plot. You're going to go to that very first item here. And again, if you go to zoom 9, there you see the scatter plot, right? And if you do trace, you can actually see the individual values there. And you can see that the scatter plot is trending upwards, so as there are more powerboat registrations, there are also more manatees being killed, right? So that's how you do the scatter plot. Now, how about the linear regression? Well, for the linear regression, you would go to Stat Calc, and you could really choose either of these, choice 4, LinReg, or choice 8 linear reg. The only difference is this is the first choice is ax plus b, and the second choice is a plus bx. Remember, wherever there's an x, the coefficient of that number, that's going to be the slope of the regression line. And the number by itself, that's the y-intercept. So here, b is the y-intercept, but here, a is the y-intercept. Otherwise, they work the same way. I'm going to use the choice 4 here. You know, you put in L1, L2, and then you could calculate that. And see, since I had my diagnostics on, I get my r squared and r value. And you could always get, if you have an r value, you can always get your r squared just by squaring this number. And you could write your regression equation. The slope is 0.12. And you should know how to interpret that, but that was for a different day, right? And that's basically how you do your linear regression. Finally, confidence intervals and hypothesis testing. We did a lot of those, but just to refresh your memory, you're going to find all that stuff in stat tests. And basically for you would only use from 1 or everything here we've learned all the way down to choice B. Once you get to choice C, the chi-squared, you don't need to know that for the test. So anything from the first choice all the way down to B, that's fair game for you. Anything below that, you don't need to know. Now, I did give you one question. It really had nothing to do with this. It was just a good question to do for homework. It shouldn't take you more than 10 or 15 minutes, so please try that out. It'll be worth your while.